You can see my slides in presentation mode and you can hear me. Excellent, thank you. And thank you very much for the invitation to be part of what has so far been a very interesting and fascinating workshop. And I'm looking forward to the next couple of days too. What I hope to do here is just share some of the background and context and foundations of the success that has often referred to in in the area of crystallography, which we heard sort of touched on in some of the chat yesterday as well. Central to what I'm talking about is going to be the Cambridge Structural Database, which will be familiar to many of you. It's now got well over 1 million crystal structured data sets. Many of them are associated with journal articles, but an increasing number are being published directly in the CSD these days. One of the key things that the CCDC does is make sure that these data sets have been enriched sufficiently to enable discovery, interoperability, and importantly, reuse across domains to tackle challenges that are relevant to both industry and academia. So key to the success of this has been a number of different enablers. The technical side, it's about standards, but I think metadata is important and persistent identifiers. That only takes you so far. You need joined up workflows that enable easy publication of the data and allow it to be enriched. And importantly, you need some social enablers that encourage people to actually take advantage of what is out there. And I'm going to touch on each of these. Thinking about the facets of a crystallography experiment, and I think this can extend to many different types of experiment. You're going to have a sample. That sample is going to have a backstory as to how it was synthesized. It's going to have various other properties that might have been measured or determined along the way. You're then going to have your instrument, which might be something sitting on a desktop in your lab, or it might be a great big facility that you've sort of booked time for. That's going to have a make, a model, it's going to have a particular configuration, it's going to have certain conditions surrounding the experiment that you're undertaking. That experiment is going to generate data. You're going to have your raw data that might get processed before you derive a model. The model is maybe going to have quality metrics. It'll have certain facets that are relevant to the particular experiment that you're doing. Software sort of pervades all of this in terms of generating the data, analyzing it, creating the models, and that has versions, it has parameters you might use and restraints, and then ultimately you get through to publication, and that might be part of an article or it might be as in a data set in a database as we've talked about there. So crystallography is blessed because it has a file format that allows you to capture pretty much all of that, even right down to the text of the article if you're publishing through IUCR, for example. But it's not just a format, it has dictionaries that underpin that particular format that semantically define the concepts that you are publishing. Now, CIF was based on a more generic system called STAR, which was developed by Sid Hall. And you may not be able to see in the small print there, but yeah, he kind of set out to create this self-defined file format that would make sure that all the data items in there could be understood by humans and by machines as well. Very much ahead of its time. It also provides flexibility. So there are dictionaries available for chemical crystallography, specific dictionaries for powder versus X-ray, and then different sort of forms of dictionaries for structural biology, MMSIF particularly, but that's been extended to account for a range of different experimental techniques. And then you can have dictionaries that define certain aspects such as the restraints you've used, electron density, and even the image data that comes off the machine. I want to say a little bit about how CIF is sort of maintained and what has encouraged its adoption. The IUCR played a very important role in this, and today the sort of maintenance and development of the framework is overseen by a committee for the maintenance of the CIF standard, or ComCIFs. When we think about adoption, there are three things that I'd point to. One is policies coming from publishers and repositories saying to people, if you're going to publish a structure, it should be published as a CIF. The other is validation tools that allow users to upload their structure, get feedback on its consistency and completeness. And this gives them some value. It gives them a reason to do this, particularly when you combine that with publishers saying you need to make sure that your alerts are explained. And I think IUCR played a role here in issuing guidance that was picked up by publishers and repositories to make sure this was being done. But I think one of the most important things that has enabled compliance is what the software packages that are being used do. Some of you will be aware of structure factors, which is the reflection data that initially weren't always published. It's important that they are because it allows you to better validate the data that's out there. And it was a challenge to get people to do this. What made it happen almost universally was when software just started including these in the files by default. The researcher may not even know this was happening, and that's certainly a key enabler. Thinking about new frontiers, there's a couple I could point to, but I'm just going to highlight one. And we're starting to look at how we can develop SIF to use it for capturing simulated crystal structures. And that's been interesting because it takes us into what I would consider the wild west of computational chemistry. And I think that's maybe a shared challenge, is how do you rigorously capture the methods that are being used in computational chemistry and the order in which they're being applied. So when it comes to having generated your SIF, how does the researcher get it out there? Well, at the CCDC, we provide a deposition service that tries to guide the researcher through the steps that they need to follow. It checks that the syntax of their file is okay. It will shell out to CheckSIF to make sure that to generate the report that might be required. It will encourage the researcher to provide additional metadata that might be useful down the line. Ideally, we'd like to see researchers depositing at their earliest opportunity when they're most engaged with that data. A lot of the time it will happen as part of journal publishing workflows, but journals would encourage deposition prior to submitting their manuscript. Once the structure is published, we'll assign DOIs and make sure the data sets can be linked to associated articles, but we'll also undertake that review and validation of the data to enable that reuse and interoperability. And a key part here is assigning a reliable representation of the chemical structure of the sample studied with that particular database, with that particular data set. I'm showing this slide to kind of make a couple of points. One is just to illustrate the sort of diversity of ways in which we can link out to different publishers to make sure that data sets are associated with articles. The other is to show the many different ways in which we have to interact with publishers to achieve that. Now, there has been an effort within the publishing industry to come up with a standard framework that enables this. Thus far, one publisher has adopted it. Thankfully, that hasn't increased the number of ways we have to interact, but it certainly hasn't simplified that. Key to all of this are standard identifiers. We'll all be familiar with DOIs, and they provide a convenient way for people to be able to link out to a particular data set, but there's a lot more to it. The metadata that you associate with a DOI provides a solid foundation for reliably citing your data. Combine that with ORCID as well, you get reliable disambiguation of authors. But that metadata also, if it's made available, can be harvested by other services to enable interoperability at that sort of higher non-specific, domain non-specific sort of level to connect together different research objects. And there are lots of different standard identifiers out there for identifying organizations. There's efforts to understand the metadata you need for identifiers associated with instruments. You can use DOIs for software, identifiers for samples and antibodies and chemical structures. And there's an effort going in here to connect all these together. And I think key message here is making sure that identifiers of various objects involved in the research are collected, exposed in metadata to be able to build out these knowledge graphs. One way we use identifiers here is to connect out to the raw data. At the CCDC, we don't store the raw data. In chemical crystallography, there's a lot of debate going on as to when it's worthwhile to do that. In this particular case, microED is sort of newer method. People thought it was worthwhile making that data available. They put it in Zenodo. We can link out from the CSD to that particular data set. The other thing we like to do is to be able to link out to other chemistry-related sorts of resources. So we have a biopesticides database, a food database. We have the ligands in the protein data bank, drug bank, and general chemistry information in PubChem. And what enables that is INCHI. And I just want to say a little bit about INCHI in my capacity as Secretary of the INCHI Trust. Now, for those that don't know, the aim of INCHI is to be able to take two different but equivalent representations of the same chemical structure, come up with a standard string that allows then searching across resources and linking across them in a reliable particular way. And yeah, it's that linking thing that I think we found that it's been most useful for. But I just wanted to sort of like delve a little bit into how the INCHI has evolved and how it's maintained today. It started off as a project within IUPAC, but has since been sustained in partnership with the INCHI Trust. So IUPAC still provide the scientific oversight and sort of like the innovation around INCHI. That's undertaken through the IUPAC divisions and committees. The INCHI Trust brings together people who have been willing to contribute money and time to actually enable the development and maintenance of it, promote its adoption. The real work takes place, though, with the sort of INCHI Trust members and supporters and project group participants. And I'm not going to pretend that INCHI is a finished project, and it works very, very well for organics. But as soon as you get out into organometallics, nanomaterials, all these sort of things, there's work still to be done. The other important piece of this is making sure that the code that generates the INCHI is sort of like sustainable and is maintainable. And that's why recently we've appointed a technical director to support that activity. So all of the things I've talked about, I think, are not just key enablers of successful data publishing, but key enablers of fair data. And if you kind of look across the sort of facets of fair data, things like identifiers, metadata repositories, I think you can see how the sort of technical enablers and the standards, etc., that I've talked about can help enable all of that. There was a slide yesterday that said, well, why, right? What's important? And I think this slide illustrates this quite well. Those million of crystal structures that have been collected over 50 years have enabled people to innovate in a whole range of areas, to get insights into fundamental aspects of molecular geometry and interactions and how molecules assemble, but importantly apply those to traditionally drug discovery, but increasingly more in sort of materials design and development. I'm not going to say it's game over. I think one of the real key challenges now is understanding how we can link out from the CSD to collections of property data that you can use to develop models that will really allow you to take advantage of AI machine learning methodologies. How you link is one thing, of course. Getting access to well-described quality data that is useful, I think, is another, and I think that's quite a big challenge. So that concludes my tour. I think in terms of acknowledging it's the scientific unions and those who sponsor them to kind of actually develop the standards. I think it's important to recognize scientific unions don't have a lot of money, so that additional sponsorship really does matter. It's the people who invest time in developing and promoting the standards and tools, often voluntarily. It's the organizations that make sure they get used in joined up workflows, and importantly, make it easy for the researcher to be able to comply. And then it's those researchers who actually do the best they can to share their data using the best available methods to enable that discovery of new insights. So that concludes my talk, and I'll happily take any questions.